Welcome to Study Loop.
So for this problem, we want to keep our whole objective in mind. So we have a swimming pool, and this is going to be a view of it, where this is the water, right? So we know that it is 3 feet deep. It's going to be 40 feet long. And then we'll have, it's going to be like a rectangular prism. So we'll draw that real quick. And we see that it's going to be 20 feet wide. So based on this, we also see that it's 3 feet deep at a shallow end, but then it's 9 feet deep at the deep end. And we have a cross section shown in the figure. So if we know the pool is being filled at a rate of 8 feet cubed per minute, so right there we want to stop. We want to recognize this is a rate. This is a change in volume because it's feet cubed per minute. So this is dV dt, a change in volume with respect to time. And that's going to equal 0.8 feet cubed per minute. And when we use it in our calculations, we're going to use 0.8 as long as the units all work out. Then we want to determine how fast the water level is rising. So right here we're given our change in volume with respect to time, and we want to know a change in height. We want to know the water level. So the water level is this right here, or this right here. This is just a height. It has nothing to do with the volume. So that's dH dt. This is what we want. So what it's up to us to do is to determine the relationship between the volume and the height. And depending on the cross-section, that'll have a different relationship. So what we do is we find the relationship between the volume and the height, and that'll be some equation. Then we differentiate that relationship, and once we differentiate the relationship, we will have an equation that we can get in terms of dH dt that will be equal to something in terms of dV dt, but we already know dV dt. So once we plug this in, that is how we are going to get dH dt, which is the water level rising at a certain point. Now, one other step we're going to have to take is we need to know what's happening exactly at 5 feet. So we need to figure out the time at which it reaches that 5 feet. So in order to do that, we have to know the height when 5 feet. Once we have our relationship between volume and this, we plug in our 5 feet here. That gives us the volume here at 5 feet, and then that goes into our equation, which will then give us the actual rate of change.